facility. Let's say you have a new protein, nucleic acid, a lipid, or a complex thereof, and you have a lot of biochemical data, biophysical data, but you don't have a structure. But no structural information is available. And in that case, maybe you can use my facility, but you have few milligrams of the pure protein. Pure is important. If you are not pure, we can't crystallize. Therefore, one of the, as you know in chemistry, one of the ways you actually purify a product is crystallizing. Therefore, you really need to have a pure, few milligrams of a biomolecule of your interest. Then we can provide you with a three-dimensional structure. Why do you care about three-dimensional structure? Why should you need it? I mean, you have a lot of biochemical data, you have biophysical data. If you have a three-dimensional structure, you can solve or use the predict mechanism, the mechanism which will be predicted. You can make sure it is exactly what it is, you can confirm it. If it is a structural protein, you can find out which ones are associated with other ones because you have a three-dimensional structure. If it is a drug molecule binding to your biomolecule of your interest, you can find the binding details and all those things you can do. Therefore, three-dimensional structure, I've just given you some idea of what we can do with a three-dimensional structure. Okay. Therefore, what the X-ray facility can do for you, we can do a lot of things. If we have a protein, we can grow the crystal for you. This has been one of the hardest stumbling block for my facility because it is not like any other core facility where you go and give your protein, immediately you get a result. It can take anywhere between 1 month to 6 months to grow a crystal. Therefore, people really don't come to my facility. They try to shun away from me. Even if you meet me in the corridor, they say, I'll talk to you later. Therefore, what we decided to do is, instead of begging people, we decided to buy a robot which can actually set up a 200 nanoliter drops in one single shot within 5 minutes. It can try 300 conditions for you. I'll show you a picture of it in the later. Therefore, instead of begging people, we tell, okay, look, we have a way to do that. Until now, people thought graduate students are like robots, but we have real robots. And therefore, we can grow the crystals for you. If that is the one stumbling block we can remove, we have started removing. About 1.5 years ago, we got a robot which does this. Interesting thing is, moment we got the robot, hey, I used to look at 24 conditions before in the microscope. Can you build me a robot to image it using the 300 conditions? Now we are building a robot ourselves to image it. But we can grow the crystals for you. As I said, it can take anywhere between 1 week to 3 months to 6 months, depending upon your protein. Then we can collect the X-ray diffraction pattern for you. That usually takes about 3 days if you collect at my home source. We also have what is called the synchrotron source in Oregon National Lab, where FSU is part of we have bought into a timeshare. We have a 10,000 times more powerful X-ray at APS, which is the second brightest source of X-rays in the world, next to only to a source at Japan. And then depending upon your collecting at home, it could take 2 or 3 days, or in 1 hour to 30 minutes at APS. That's all done remotely. You sit at home and send your sample. This is called FedEx Data Collect. You send the sample via FedEx. They have a robot which puts in the sample. You sit at your home, connect a computer, and then you're given a time. You can collect from home. You control the machine at APS, an advanced photon source in Oregon, Illinois. We can either collect at home or collect the diffraction at APS, and then we can process the data for you. The diffraction picture gives you only the intensities, but we need the electron density, which needs the phases, which I don't want to go into details, but if some of you are familiar with, that is the biggest problem in X-ray crystallography, especially protein X-ray crystallography. And then we can get the electron density map for you. That is the interaction of X-rays with your protein of interest is usually electrons. That's what you see, the kind of chicken wire thing. That's what we get for you. This could take anywhere between 3 to 6 months, depending upon what it is. It's a very broad range, depending on how hard it is. And then we can solve the structure for you. Based on the electron density, we can get a three-dimensional structure. As I said, once you have a three-dimensional structure, lot of things you can understand, where your drug is binding, why your protein is behaving a certain way, all those things can be done for you. This is basically in a nutshell what I can do. Therefore, the X-ray facility can help you in the steps 1, 2, 3 and 4 depending upon how much you are interested in. There are pure crystallography labs which they come, use the facility and get out. There are labs which you want to learn, we can train you as much as you want our help, we can train you as much. If you don't want, we can just let you, like somebody said, like Laurent said and Rivera said, that we can help you if you want. If you don't, I'm the only guy in the facility. Therefore, if you want my help, I can help you. If you're on your own, you can do it. And with the crystallization screening, I'm just going to go through a little bit of detail. We can screen the crystallization. What does it mean? You have a protein, but you don't have a clue where it is going to crystallize. We have a commercial screens, 1,000 different conditions, which is already pre-prepared. We mix your protein with 1,000 different conditions to see whether it will crystallize. That is what the crystallization screen means. That has been automated using a nanoliter robot. That means it takes a nanoliter, 200 nanoliter of your protein, mixes with 200 nanoliter of your unknown commercial screen, wait for about a few hours to a day and see whether it crystallizes. Otherwise you move on. Therefore you can set up about 300 to 1,024 conditions and check it for you. And then once you have some hits, that means the clue that's crystallizing, we can optimize by narrowing the conditions in which actually initially crystallize for you. Then we can image the crystals, and then we can do it either room temperature 4 degrees or 10 degrees, whatever we want, and then we can store the crystal for you at 100 Kelvin. As you know, biological molecules are very, very sensitive to X-rays. Therefore, about 20 years ago when I started this field, we were collecting everything in room temperature. Now, everything is collected at 100 Kelvin. All the data, whatever I say, everything is collected at 100 Kelvin. Okay, we have a home source, which is a copper rotating anode with a wavelength of 1.54, which happens to be the carbon distance, works very fine. And then we have a cryostream cooler, which makes all the sample at 100 Kelvin. We have an R-axis image plate detector and a MOSFET. These are two automated detectors. We can, as I said, automatically collect data and process. And then we can either do room temperature or cryo. As I said, 99% of the time we do 100 Kelvin data collection. We also have a dedicated beam line at SERCAT, Southeastern Regional Collaborative Access Team. It is an advanced photon source at Oregon National Lab, beam line 22. We have two beam lines, ID and BM. We have 24 hours every 4 months. 24 hours is a lot of time. What you collect at home in 3 days, you can collect in half an hour. And then we have a dedicated proposal-free beam time. That means we already have a time. If you want to collect, you don't even have to write a proposal. As I said, FedEx shipment, you put the samples in one of those cryo shippers, send it to them. They have 120 space holder in the robot inside the hutch where the beam is coming. You can sit at home, click one by one and check whether your sample is refracting. Once it is collected, we can actually do the data processing also in Oregon. That means you're sitting at home doing everything there only during your time and only get the final data of the diffraction data at home. And then you can do the data analysis, three-dimensional modeling at home. And this is my final slide. I'm just going to give you the details. That is the robot right there. That sets up about, the tray is sitting right here, about you can have 300 conditions right there. That is the 96 different buffer conditions. And you can have 3 of the 96, close to 300 conditions. And it can set it up 200 nanoliters at a time. And then we can see and look at a day or week later. And this is our X-ray home source. This is our R-axis image plate detector. This is our X-ray generator right here. And then this is the advanced photon source in Oregon National Lab in Illinois, where we have a 10,000 times more powerful X-ray than I can generate at home. Therefore, everything gets done very fast. And as I said, we have dedicated time. Therefore, to summarize, that is our facility, biophysics, X-ray facility. We can refractive crystals, and we can do the screening, diffraction screening, optimization, data collection at home.